Alrighty, so we have some help bringing us into lecture set 9 on the three-body problem. And yes, so it's kind of interesting. I'm sure you have seen that, the two-body problem is so simply solvable in terms of our conic sections, and the three-body problem is in general unsolvable. There are these sort of special cases, these sort of just so analytic solutions, like this figure 8 that I'm showing down at the bottom. Also an equilateral triangle of three bodies that are all sort of orbiting around some center of mass. But, just perturb them just a tiny bit, and they turn into something else, something much more chaotic and stochastic, and very, very sensitive to small changes in the initial conditions. You can learn a lot about chaos theory and fractal structures. If you plot the initial conditions against one another, you'll get fractal-like things. If the color depends on what the final state of this thing is, you can get sort of fractal Mandelbrot set like diagrams from this simple three-body problem. So the way we will tackle it in this class is to simplify it in terms of something we call the restricted three-body problem. So we're going to think of a hierarchy of masses. So the first two objects basically are massive. They exert a gravitational force. The third body has a very, very low mass. It's just considered to be a test particle that doesn't exert a gravitational force back on the other two. So solving the problem of M1 and M2 goes back to the two-body problem. And we can simplify it even more by going from the restricted three-body problem to the circular restricted three-body problem. Sometimes you do see this weird acronym for it. But that simplifies a lot of things and makes it a much more mathematically tractable problem, but also is applicable in lots of situations in astronomy and planetary science and space exploration. If you're sending a spacecraft in the vicinity of a star and a planet, or a planet and a moon, the spacecraft acts very much like that massless test particle M3. Same thing about motions of stars in a galaxy. If there's a neighboring satellite galaxy that's also sort of in orbit around it. The middle bullet here is another interesting special case because we can think of this little test particle just as a parcel, right? When we talked about fluids and MHD, we talked about parcels of gas and how they move and what are the forces on them. Well, if you've got this close binary of two massive objects, the fluid parcels that form the surfaces of those stars, say, are going to get distorted by the mutual forces and the rotation, so that you can think about these test particles as little pieces of the surface of these stars. So by solving this problem, we can also figure out what are the shapes of distorted stars in a binary system. All righty. So what do we do? Right, so we are assuming that M1 and M2 are in a circular orbit around one another, around a center of mass. We can take that center of mass as the origin, and we will see that things get much easier when we actually transform into the rotating frame of that M1, M2 binary. So we'll be thinking a lot about the angular rotation rate of that binary system, capital omega, which we can think of as a vector. And that vector is pointed, you say, in the z direction, right? If the binary is in the xy plane, the angular momentum and also the angular rotation vector is normal to that plane. We know how to write that for a nice circular orbit for a two-body system. We've been doing that a lot. And, well, we have to write the full Lagrangian for the three-body problem. But we'll see we can simplify it a lot. But we've seen this general form before. We've got the three components of the individual kinetic energies, summed over the three particles. minus the potential energy. And we've shown how to write that in terms of the unique pairs. And the three-body system is interesting because for three bodies, there are three pairs, right? There's a triangle of interactions. And, the shorthand here, R sub ij is just going to be the magnitude of, the distance between Ri and Rj. Right. So when we do it, when we write out this Lagrangian, we find that many of the terms in it are constants. For example, if we eventually go into the rotating frame, we'll see that particles 1 and 2 are really just sitting there. They're just, they're not changing their R dots, right? They're not changing, there's no change in the relative distance between them. There's no change in their, they might be moving around in theta, but that means that the theta dot is a constant. That's this angular rotation rate. That's also a constant. So for particles 1 and 2, the kinetic energy terms are just constants of the system. Also, the first potential energy term is also a constant because it only depends on R1, 2. And again, for a circular orbit, the distance between 1 and 2 is not changing. And you can follow this up if you really want to see the detailed derivation. There's this very detailed paper by Haji Dimitriou from 1975. I'll put a link to it in the description. But the reason we're focusing on these constant terms in the Lagrangian is because those are essentially ignorable. When we write out the Euler-Lagrange equations, we're taking derivatives of the Lagrangian. So any constant term is just not going to appear in those Euler-Lagrange equations. So we might as well just ignore them. We can just as well assume those constants are 0 in the Lagrangian. Well, if we do that, there's only one kinetic energy term left. That's the kinetic energy of our massless particle 3. And there are two terms in the gravitational potential. You can, it's the second 2 up here. You can take out a factor of m3 and write the rest of it as a potential function, gm over r, gravitational potential that just depends on the positions of r1 and r2 and on the position of r3. But now I'm sort of writing the position and velocity coordinates basically as these are the vectors that point to particle 3 and describe the motions of particle 3. Okay, so we've got our Lagrangian. The other step is to transform the coordinates into the rotating frame coordinates. That only affects the kinetic energy term. The potential energy term doesn't change because the potential energy terms only depend on the relative distances between particles, and that quantity doesn't depend on what frame you're looking in. Relative distances are always fixed, but the velocity, of course, does depend on what frame you're in. So you have to transform. You have to say that the overall velocity in the inertial frame is given by two components. There's the velocity in the rotating frame, and there's the velocity of the rotating frame, which is given by the cross product of this omega vector crossed into the r vector pointing to the particle. And hopefully you can see from the cartoon why omega cross r gives you a vector that is always pointing, in the direction of motion of that rotating frame. Those red vectors are tracing out a circular path. And the units are velocity, of course. Right, so that tells you how to make that transformation. Now, at this point in the derivation, I'm going to sort of pull a trick and basically remove all the primes from the rotating frame coordinates, because if we're going to be operating in the rotating frame, let's just choose that frame for our simpler unprimed coordinates. So at this point, all of our r's and r dots are going to be, yes, we're going to refer to these rotating frame coordinates, but we're going to call them just r and r dot. And then we'll write the Euler-Lagrange equation to get our equation of motion. And we can do it all in one in one go here. We can write it as vector gradients rather than individual partial derivatives of each component. There's other ways of doing this. I'll have a link to Marion's textbook that shows another way of deriving the equation of motion in the rotating frame. If you've seen it before, you might have seen it done in a way other than using the Euler-Lagrange equation. But it is kind of elegant to see how you can do that. Well, I can just sort of trace out the steps of the derivation. At the top, I'm just sort of showing the Lagrangian as we simplified it and the differential equation we want. So we have to actually perform these derivatives of the Lagrangian. And well, the one thing we have to do is also substitute in this velocity for the two-part component, right? The changes with respect to the rotating frame and then the motion of the rotating frame itself. This magnitude squared is really going to be a vector dotted into itself. So it contains a whole bunch of different terms, in a products and a sum, and we can use some vector identities to transform them a little bit. I won't go through the derivation, but what we need from this is to take the derivative of the Lagrangian with respect to r dot, and there are various places now in this kinetic energy term where the r dot appears. So there's a r dot squared that just becomes a sort of a momentum term. And then there's an r dot sort of embedded in this middle product. And the answer ends up just containing an omega and an r in a cross product. And then to get the right-hand side of the Euler-Lagrange equation, we have to take the time derivative of that, which just involves adding another dot to each of the r's. The omega, if we remember, is just a constant, so there's no time derivative of that to worry about. All right, that gives us the right-hand side of the Euler-Lagrange. The left-hand side involves taking derivatives with respect to the spatial coordinate r, which is now again the spatial coordinate in the rotating frame. There's a gradient with respect to the gravitational potential due to objects 1 and 2, and then there's a bunch of other r's that appear in the v squared, and you have to take that derivative too. It ends up looking like this. So then when we put together the two sides of the Euler-Lagrange equation, there is some simplification, some combining of terms for the omega cross r dot, and then each term has an m3 in it, so we can cancel those out, and we get a nice equation of motion for the rotating frame. And I'm sure you've seen this before, right? If you forget about the gravitational potential, there are these extra, sometimes called fictitious forces in it, because if you're in this rotating frame, you're in an accelerating frame, and you're feeling the effects of that acceleration. The term that involves the r dot is the Coriolis force. The term that involves just the omega and the position is the centrifugal force. And it actually turns out to be easier to write these out in Cartesian coordinates. If we define the z-axis as the rotation axis, then the xy plane is the plane in which the m1, m2 binary is rotating. So the left-hand side is just the second derivatives of x, y, and z coordinates, remembering that x and y are coordinates in the rotating frame. Z doesn't care about that. I put the gradient of the gravitational potential first. Then there's the Coriolis term that involves x dot and y dot, and the fact that the x equation has the y dot and the y equation has the x dot. If you've ever played around with the Coriolis force, it's a very sort of twisty, turny thing that, if you're talking about motions in this direction, the force is in some other direction. It's a little counterintuitive. The centrifugal force is a little easier conceptually to deal with. The x term has an x, the y term has a y, because if you're just looking along the x direction, the Coriolis term is out. If you're looking in the y direction, it's out. Any direction that you are, it's out. All righty. So there's all these different forces happening on the right-hand side that it's important to try to understand. Mathematically, Roche simplified the problem a bit by noticing that the centrifugal terms on the right-hand side there can be written as the components of a gradient of a scalar function. So you can now define an effective potential that has both the gravitational potential and this other centrifugal potential. And then when you take the gradient of that, you get the exact, you get these exact terms, centrifugal terms, and there's no z component, so there's nothing in the z, so that we have simplified the equations of motion even more to get rid of those centrifugal terms. So they're, and we can actually simplify them a little more. Well, soon we'll take those Coriolis terms seriously and look at their implications. But right now, let's just sort of restrict our field of vision here for what we want to do. Let's look only at the equilibrium properties of the system that involve how does the system behave, what's the physics, what are the forces when particle 3 is at rest in this co-rotating frame. So that says, all right, what happens when we set the x dot and y dot, the horizontal velocities of the particle 3 equal to 0 in the rotating frame? All right, yes. So we'll soon look at the full problem with the Coriolis forces in them, but without the Coriolis forces, the equation simplifies down a lot more, and it becomes much more straightforward to write it in a vector notation. And what this really means, you've got an acceleration on the left-hand side and the gradient of a potential on the right-hand side. So this basically tells us in 3D space, the acceleration on the particle depends on the changes as a function of space of this scalar function, this effective potential that takes on values as a function of x and y and z. But if you're moving around and the effective potential is changing very rapidly, that means there's a big force in that direction. But if you're moving in some other direction and the effective potential function is constant along that direction, there's no force, right? So you can sort of map out three-dimensional contours of the scalar effective potential. And if you're moving along one of those contours, there's no force on you. If you're moving in the normal direction to the contour, there's the maximum force, right? That's the direction of the acceleration, the direction the acceleration is pointing, right? And I mean, you've seen this before, of course, right? For a point mass in isolation, the potential is really just the gravitational potential, and these equipotential forces are just spheres centered around the gravitational point mass. This is why the surfaces of stars and planets are spherical, because all the mass, all the parcels are orienting themselves sort of piling up along these equipotential surfaces. Okay, so in the next video, we'll look at it a little bit more for this case of the rotating system of two different masses, and we will see how things behave.